A periodic short-term variation in Meteor shower fluxes, and it has way too many slides, so I will start immediately. What is the motivation for this talk? Well, about 20 years ago, correctly speaking, in 1999, we had some scientific debate about video observations that we did from the 1999 Leonid storm, ground-based observation, different cameras, and when we analyzed these data, we found clearly some periodic oscillation in these data. And we did some wavelet analysis, and there was a clear outcome that we have certain preferred frequency, that the activity was like oscillating with a frequency or with a wavelength of about 7 to 8 minutes. It was not only visible in video data, we even had radar data, which were showing these periodic oscillations. But then when we wanted to present the results on some Leonid conference in Israel, our paper was not accepted. Reason not known to me, I suppose. It's because only our ground-based video data show these or have shown these periodic oscillation, whereas the airborne video data did not show these. At least that was my idea or my thought by that time. And now the question is, 20 years later, 20 years more of wisdom that we have, 20 years of tools that we now have. Well, if we do the same analysis on the old data, would we come to the same result? And if so, was the Leonids 1999 the only shower where we have these kind of periodic oscillations? Or are there maybe other showers which show a similar behavior? All right, and in order to answer this question, 3 things have to be done. Well, starting from the old 1999 Leonid observation, at first have to be able to collect all the relevant data that I need to calculate flux densities. Then the second part is to import these data into the Meteor flux tool that I can visualize again the flux density. And then the third thing, I need to implement some frequency analysis which Meteor flux didn't have so far to check for these kind of periodic oscillations. So let's tackle these 3 tasks. The first one, do I get all the relevant data to calculate flux densities from these 23-year-old observations? Well, most of the thing can be calculated on the fly, like the orientation of the camera, the size of the camera field of view, the resolution, and so on. The effective collection area, that can all be done easily. The most critical part is the limiting magnitude, because metric is calculating the limiting magnitude only on the fly. So if the observation is gone, I either have the data or they don't have it. That's really the critical point. How do I get the limiting magnitude? And what I've done effectively is I've taken the Meteor records that we have with some images and calculated the limiting magnitude from these some images. So I created 2 little helper tools which would allow me to create nice sum images for more than 1 meteor, and then to measure the limiting magnitude here. And of course, this method works only if your limiting magnitude is more or less constant during the observation. But by that time, 1999, 2001 Leonids, we had perfect observing condition at our observing sites. So if I have once the limiting magnitude, I can safely assume it was constant over the whole observing time of 2 or 3 or 4 hours. So that was the first thing to be solved. Then the second thing, how do I import the data into the Meteor flux tool? Well, fortunately, the data format that Metric is using has changed only very little over the last 20 years. So more or less with some manual tweaking, I was able to import the old log files into the latest software and creating a limiting magnitude file manually and loading everything into the Meteor flux tool. So that worked out with some, as I said, with some manual tweaking. And then, of course, I had to do some slight adjustment of the user interface, because that typically starts at 2011. That was the first time when we did Meteor flux observations. And now I have put in a little button here, which is called Use Historic Data. And that allows me also to go back further, even to 1999, in case I have uploaded this kind of historic observation before we really measuring limiting magnitudes on a regular basis. So that was point number 2 solved. Now we come to point number 3 about the frequency analysis. Yeah, well, that's more or less standard, but on the other hand, it still has to be implemented. So what we did back in 1999 was to do a wavelet analysis. We were using some professional tools that Jürgen had provided. It has some advantage of wavelet analysis. So you can, for example, measure variations in frequency over time. So if the frequency is changing, that's something which you can done nicely with the wavelet analysis. You may have different resolution, time resolution for different frequencies, and you can select also other mother wavelets for this wave analysis, which is not the sine curve, but actually for what we are doing here, it is fully sufficient to do just a standard Fourier transformation. because we are looking only at short time intervals anyway, and there's no good reason to assume that another mother wavelet than the sine wave would be the best one. So what I've implemented in Meteor flux is just a standard discrete Fourier transformation. Two things that I learned about this, what you really have to be careful, the bin size has to be fixed. So those of you who know the Meteor flux tool, they know that you can adjust the bin size. When you have less data, you're using large bins, and when you're close to the peaks, you can use small time intervals. That will not work out. So you need to have a fixed bin size, and there should be no gaps in the flux density graph. So if you have observations from 2 nights, nighttime, daytime, no observation, another nighttime, of course, what you are doing with it, missing data in between. So that's also not working very well. It should be one piece, one period of time where you have constantly sampled flux densities. So again, the third thing is solved. Just click on the frequency analysis button in the Meteor flux tool, and then you're ready to do frequency analysis. So one last word, topocentric correction. So what is this all about? When David Escher and Rob McNaught did their predictions from the 1999 Leonid storm, they said, well, it actually matters where on Earth you are observing. So why is this? Because we are talking here about really very short time scales, about a few minutes. And they're serious. You have the plane, the orbital plane. So there the density of dust is higher. And then the Earth is cross-sectioning this plane. And then, of course, the guys who are sitting close to the southern part of the Earth, they're crossing it earlier. They will have the peak time a little earlier than the guys who are on the northern hemisphere. So this is what they came up with for the 1999 Leonid prediction. So, and that is in the range of a few minutes that guys observing in the south see it earlier than guys observing in the north. So I believe that the topocentric correction that we need is a little different, because I believe it's not relevant for these kind of periodic stuff at what time you're crossing the plane, but I believe that within the plane you have certain denser parts and less dense parts. So it's relevant at what time you reach a certain part within the dust stream. And so the formula that I came up with, and I hope that someone can confirm, can think about it and confirm it, I believe it's just the sine of the radiant altitude, because that says if the radiant is in zenith, then I'm really on the top front part of the Earth and I'm crossing the dust trail first. Whereas if the radiant is low or even below the horizon, then I'm at the back part of the Earth. So this is a kind of formula that I came up with. Actually, it's not working out. I can tell you that already in advance. I have tested my flux calculations or the search for periodic variations, both with and without this correction, and it doesn't make any difference. So it still may be wrong, but at least it's a proposal, and I would be glad if some clever guys think about it and maybe tell me you are wrong. The formula should look a little different. All right, now let's come to the results. So as I said, the first thing I checked was again our old 1999 Leonid observations. By that time, we had observations from 4 different sites, one in Jordan, 2 cameras in Spain, another 2 cameras from English observers in Spain, and 1 camera on Tenerife. All right. And again, this is now the flux profile that we get with Meteor flux. And this is what we get from the frequency analysis. So you see, indeed, there's standing out very clearly one frequency with a wavelength of about 7 minutes. Here are the next most relevant frequencies. So yes, we can confirm definitely in the 1999 Leonid storm, we had some periodic variations with a frequency or with a wavelength of about 7 minutes. Right. So that was the first Leonid storm. And by the way, if you look in the individual sites, so the first one was a summary of all the observations. So also looking at the individual sites, so the 2 cameras at Tavira, the 1 camera at Tenerife, the 2 camera in Malaga, they all show these 7 minutes. More interesting already, 1 camera, which was in Jordan in a way, has a slightly different frequency. So it's not about a phase shift, it's really that was more like 6 point something minute. Interesting, but at least definitely the average shows there's this around about 7 minute variation. So what about other showers? Well, we do have, of course, another Leonid, or we had another Leonid storm back in 2001, which I had not analyzed so far. Again, the same things apply. So if I am able to calculate the limiting magnitude for this camera and they had good observing conditions, I can reconstruct all the data that I need to load it into Meteor flux. And here we have a bunch of cameras which were operated by that time. most of them in Asia, a few of them also in the Americas. So by that time, remember, we had like 2 dust trails which were passed. And once more, we see clearly that the first dust trail, the 7067, which was visible from the Americas, was from the flux density clearly lower than the second one that we observed from Asia. So, and now the interesting moment comes. Do we see any periodic stuff? No, unfortunately not. We see a number of frequencies here, and I always mark this 7-minute here that we have seen in the 1999 one. And yes, every now and then you see some frequencies. I mean, this is here now again for the different observing site. This one, the Americas, this one here in South Korea, this one in Mongolia. You might have seen, yeah, you might think here in Mongolia could be close to it, but there's definitely no clear sign for one frequency. And now I quickly jump to other slides because, of course, I was curious. I was looking for other meteor showers. I was looking like at later Leonid observations where we have a limiting magnitude. We have 3 years where we have a sufficient sample, 2017, 2018, 2020. And this is like a spectrogram. And again, you see, yes, you seem to have some frequencies which are more prominent, but I would not really say there's one clear prominent frequency visible in the other Leonid data. What about other showers? Let's have a look at the 3 big ones that we have in the course of the year, the quadrantides. Well, you know, here we have some peaks at 17, 12 minutes. In this return, 2014, no clear. At this return, you have one frequency. The last interesting picture that I want to show you is actually this one, because this is a quadrantides of 2019 and 2020. These are the returns where we really have most data, like more than 5,000 or here almost 3,000 quadrantid meteors. And this looks really nice again. So we have really 2 main frequencies which really occur most prominent, which are at wavelengths of 13.6 and 6.7 minutes. And one return later or 1 year later, exactly the same frequencies or the same wavelength. So this is really the best example that I have, which shows some similar behavior, that we really have some periodicity in our data, and I can really jump all over the other ones. This is now a number of Perseid observations. Again, you have always some frequencies which seem to be standing out, but it's always at a different wavelength. So this is here next set of Perseid data. Sorry, still no clear single frequency which jumps out. This is from 3 Geminid maxima, where we recorded most meteors, 4,000, 5,000, or even 9,000. But again, it's a mixture of many different frequency, but not really a clear sign that there would be one prominent frequency where the data is really like oscillating. Yeah, which brings me to my, all right, and we have one outburst, one more that we could record, that was the Draconids in 2018. Well, there is one periodicity, one wavelength of about 6 minutes, which stands a little out of the data. But yeah, given that we have seen before in all the other showers that things are changing from year to year, I would not be I would not have too much trust if this is really like real or yeah, some sporadic variation, say. So the summary, yes, we can load old observation into our Meteor flux tool, at least as long as the observing conditions remain constant. So we have a constant limiting magnitude. We definitely can confirm the 7-minute periodicity in the 1999 data. We could not see any further variations, periodic variations in the Leonids, neither in 2001 in the storms nor in later observations. And for the other meteor showers, I mean, of course, everything is implemented now, so everyone can play with the data. From what I've tested so far with the major showers, it was just the quadrantides in 2019 and 2020, where we had a clear sign of periodicity of similar frequencies in these 2 years. But otherwise, so far, I didn't find anything. And that's it.